It is possible to reduce the conductor size as the number of conductors in a conduit decreases. This is considered a tap if the reduction in conductor size happens where a branch circuit is taken off the main circuit. The National Electrical Code, or NEC, permits taps on a circuit if certain conditions are met. Firstly, the tap conductor must be sized to carry the load of the branch circuit. Secondly, the tap conductor must not be smaller than 14 American wire gauge copper or 12 American wire gauge aluminum. Thirdly, the tap conductor must be protected by a fuse or circuit breaker rated for the ampacity of the tap conductor. If reducing the number of conductors in the conduit, it is permissible to reduce the size of the conductors. However, it is critical to ensure the remaining conductors are still adequately sized to carry the load of the circuit. Here's an example. Imagine a circuit with 10 conductors in a conduit, and these conductors are initially sized for 20 amps. Now, at the first load, 4 conductors are dropped off. This leaves 6 conductors in the conduit. At this point, the size of the conductors can be reduced to handle 15 amps. One important thing to note is that it is not permissible to increase the size of a conductor in a conduit. The conduit is originally sized for the maximum number of conductors it can contain. Increasing the size of the conductors may exceed the conduit's capacity, violating code requirements and potentially causing overheating or other safety hazards. Always consult the NEC and relevant electrical codes for specific requirements in the given location. Understanding conductor ampacity, dating factors, and conduit fill calculations is crucial for safe and compliant electrical installations. When dealing with multiple current-carrying conductors in a raceway, the ampacity of the conductors must be derated according to NEC Table 310.15 current. This table provides adjustment factors based on the number of current-carrying conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. If there are 7 to 9 conductors, the ampacity is derated to 70%, and so on. This derating is necessary to account for the increased heat generated by multiple conductors in close proximity. The heat can reduce the insulation's ability to dissipate heat, potentially leading to premature failure or even fire hazards. Therefore, it is essential to consider the derating factors when selecting the appropriate conductor size. Voltage drop is another important factor in determining conductor size. As electricity flows through a conductor, some voltage is lost due to the conductor's resistance. This voltage drop can cause equipment to operate inefficiently or even fail to start. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, the following formula is used: voltage drop equals 2 times K times A times D divided by circular mils, where K is the direct current resistance factor, I is the current in amps, D is the one-way distance in feet, and circular mils is the area of the conductor. Increasing the conductor size reduces the resistance and therefore reduces the voltage drop. The distance from the power source to the load significantly impacts the conductor size needed. Longer distances result in higher voltage drop, necessitating larger conductors to compensate. For example, a circuit run of 200 feet will require a larger conductor than a circuit run of 100 feet for the same load. When reducing the conductor size, ensure that the reduced size still complies with the NEC minimum ampacity requirements for the load being served. The ampacity of a conductor is its current carrying capacity, and it must be sufficient to handle the load without overheating. NEC Table 310.16 lists the allowable ampacities of insulated conductors rated up to 600 volts, based on the conductor's insulation type and temperature rating. This table is essential for determining the appropriate conductor size for a given application. When making taps, use approved methods and connectors. Taps must be made in a way that ensures a reliable electrical connection and provides adequate insulation. Avoid using insulation displacement connectors, or IDCs, on larger conductors, as these may not provide a secure connection. Instead, use compression connectors or bolted connections that are specifically designed for the conductor size and material. Ensure that all connections are properly tightened to the manufacturer's specifications. The type of load being served also influences the conductor size. Motors, for example, have high inrush currents when starting, which can cause a significant voltage drop. Therefore, conductors serving motors must be sized to accommodate the inrush current. The NEC provides specific guidelines for sizing conductors for motors, taking into account the motor's full load current and starting current. Nonlinear loads, such as those found in electronic devices, can generate harmonic currents, which can overheat conductors. Therefore, conductors serving nonlinear loads may need to be oversized to compensate for the harmonic current. The NEC provides guidance on sizing conductors for nonlinear loads. The insulation type of the conductor also affects its ampacity. Different insulation types have different temperature ratings, which affect the amount of current the conductor can safely carry. For example, conductors with THEN insulation have a higher temperature rating than conductors with TW insulation, and therefore can carry more current. When selecting conductors, consider the ambient temperature in which the conductors will be installed. High ambient temperatures can reduce the ampacity of conductors. The NEC provides adjustment factors for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. The type of raceway also affects the ampacity of conductors. Conductors installed in enclosed raceways, such as Conduit, have a lower ampacity than conductors installed in open air. This is because the enclosed raceway prevents heat from dissipating as effectively. The NEC provides dirting factors for conductors installed in raceways. When reducing the conductor size, consider the impact on overcurrent protection. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductor from overloads and short circuits. The overcurrent protection device must not be larger than the conductor's ampacity. If the conductor size is reduced, the overcurrent protection device may need to be reduced as well. The physical location of the tap is important. A tap should be made in an accessible location where it can be easily inspected and maintained. Avoid making taps in concealed locations, such as behind walls or above ceilings, unless the connections are made in an accessible junction box. The length of the tap conductor is also a factor. The NEC limits the length of tap conductors to prevent excessive voltage drop and ensure adequate overcurrent protection. The specific requirements for tap conductor length depend on the application and the size of the tap conductor. Coordination with other electrical systems is crucial. When making changes to the electrical system, it is important to consider the impact on other systems, such as lighting, HVAC, and fire alarm systems. Ensure that the changes do not overload the electrical system or create any safety hazards. Professional expertise and compliance with electrical codes are vital for safe and reliable electrical installations. The NEC is a complex document, and it is essential to have a thorough understanding of its requirements before making any changes to the electrical system. Consult with a qualified electrician or electrical engineer to ensure that the work is performed safely and in compliance with all applicable codes. Consider using a conductor sizing calculator. Several online tools and software programs can help calculate the appropriate conductor size for a given application. These calculators take into account factors such as the load current, voltage drop, conductor length, and ambient temperature. They can also help determine the appropriate dirting factors for multiple current-carrying conductors in a raceway. Always verify the results of any conductor sizing calculator with the NEC to ensure compliance. Grounding and bonding considerations are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. Bonding ensures that all metal parts of the electrical system are at the same potential, preventing electric shock hazards. When making taps, ensure that the grounding and bonding conductors are properly sized and connected. Document all changes to the electrical system. Keep a record of all changes made to the electrical system, including the size and type of conductors, the location of taps, and the rating of overcurrent protection devices. This documentation will be helpful for future maintenance and troubleshooting. Consider using a circuit management software. These software programs can help track the electrical system and manage changes. They can also provide alerts when maintenance is due or when there are potential safety hazards. When working with electrical systems, always follow lockout/tagout procedures. Lockout/tagout procedures ensure that the circuit is de-energized before any work is performed. This prevents accidental energization of the circuit, which could cause serious injury or death. Always use appropriate personal protective equipment, or PPE, when working with electrical systems. PPE includes items such as gloves, safety glasses, and insulated tools. This equipment helps protect against electric shock, arc flash, and other hazards. Regular inspections and maintenance are crucial for ensuring the safety and reliability of the electrical system. Inspect the electrical system regularly for any signs of damage or deterioration. Perform routine maintenance such as tightening connections and replacing worn-out components. Address any problems promptly to prevent them from escalating into more serious issues. Always use qualified personnel for electrical work. Electrical work should only be performed by qualified electricians or electrical engineers. These professionals have the knowledge, skills, and experience to perform the work safely and in compliance with all applicable codes. Attempting to perform electrical work without the proper qualifications can be dangerous and can result in serious injury or death. Ensure proper labeling of conductors and equipment. Clearly label all conductors and equipment with their voltage, amperage, and function. This helps prevent confusion and ensures that the electrical system is operated safely. Use permanent labels that are resistant to fading and weathering. Regularly review the electrical system design. As loads change and new equipment is added, the electrical system design may need to be updated. Regularly review the electrical system design to ensure that it is still adequate for the current needs. Consider factors such as the total load, voltage drop, and overcurrent protection. Proper planning and coordination are essential for successful electrical projects. Before starting any electrical project, develop a detailed plan that outlines the scope of the work, the materials needed, and the safety procedures to be followed. Coordinate the work with other trades to ensure that the project is completed efficiently and safely. By following these guidelines, electrical professionals can reduce conductor sizes safely and effectively while maintaining compliance with the NEC.